Well, good morning. This is 8:05 on Tuesday, the 20th of June, 2017. It's supposed to be differential equations, which is Math 238. However, I'm the only person in the room, so I don't know where the students are this morning, but we'll go on and get started with where we left off. We're in section 2.1, talking about autonomous differential equations and direction fields. Thought we had pretty much beat this to death, but there's still a couple more things they want to say about it. Middle of the page 43 then. If a first order differential equation is autonomous, we see from the right hand side of the normal form dy dx is some function of y. Remember, it can't be a function of x. It has to be a function of y. That slopes of lineal elements pass through points on the rectangular grid used to construct direction field. We've already done that. Okay. Put another way, lineal elements passing through points on any horizontal line must have the same slope and therefore are parallel. Okay, slopes of lineal elements along vertical lines will vary. Okay, so if it's a function of y alone, when it's on a horizontal line, that's a function of x. There is no function of x. They are at the same y on any horizontal line, so therefore the value doesn't change there. Okay. But vertically, yeah, of course it changes. Okay. They do show a figure here, 2.1.10. It's of an autonomous differential equation dy dx. Let me get my pen in the right color. There we go. Dy dx is equal to 2 times y minus 1. Okay? Now, looking at that, I hope it becomes pretty obvious to you that anywhere y is equal to 1, the derivative is 0, meaning it's horizontal. So that means that every point here, and I'm just doing the hatch marks, you know, where the grid lines are, but anything in between, these are all horizontal. Okay? And then you can pick any other value, like y is equal to 0. The slope L along those lines would be -2. So that would be something about like this, like this, like this, this, like this, like this. All the same slope, even though mine don't look like it, but -2. That's the slope. Okay? If you go one above, y is equal to 2, then you would be +2. Greater than +1, but not super steep. Okay. And you can go on for any value of y you choose. -1 would be a -4, so that's even steeper. Okay. And so on. And +3 would be a +4, even steeper. Okay. And they go on. In fact, the higher you get, the steeper, the further away from that y equal 1, you're there. Okay. Now, they talk some more about it, but that's pretty much showing what you've got. Up here, they're almost vertical slopes. Not quite, but almost, because they're getting steeper and steeper and steeper. So your lines are basically going up very quickly, okay? And any line you do is going up very, very quickly, okay? So, now let's look at the translation property. You may recall from previous mathematics that the graph of y is equal to, let's see, I think I'll go on and erase this one because it has nothing to do with this. All right, sorry, I do have somewhat of a sore throat this morning, so my voice isn't coming across well. That's part of it. I'm sort of suspicious I might have a really low-grade sinus infection, and I think the drainage has got my throat hurting now, but my immune system is so wacko I can't tell. You know, so anyway, let's go on. Translation property. Was talking about when you had a function like y is equal to f of x minus k, that was a horizontal shift to the right, k units from what y is equal to f of x was. Horizontal shift, okay? Rigid translation, a shift, horizontal shift. The translation is to the right if k is greater than 0, and to the left if k is less than 0 because of a minus sign there. It turns out that under the conditions stipulated for the equation we're dealing with here, but you have to go back to page 39, dy dx is equal to f of y, okay? The solution codes for the autonomous first-order differential equations are related to that concept of translation, but let's take a look at this one, okay? In fact, I think I'll delete that, and we're looking at dy dx is equal to y times y minus 3 minus y. Okay, now, first glance, I hope you see when y is equal to 0, that's the x-axis, the slope is always 0. So you can draw those in right there. Slope is 0 anywhere y is 0. Also, the slope, dy dx, is 0 when y is equal to 3. So up here, you also have a 0 slope. Okay. Now, in between there, you have a variety of things going on. Let's say when y is equal to 1, you have 1 times 2. So there's a slope of 2. Okay. I'm not anywhere close to 2. When y is equal to 2, you have a slope of 2. See? 3 minus 2 is 1 times 2. So you have the same slope here as below. Okay? Now, get above that, okay, y is equal to 4, and then you have 4 times a negative 1, so suddenly here you have a negative 4 slope, really steeply down, okay? Okay, I'm not going to do all those. And when you go up to y is equal to 5, that will be a negative, oh boy, 5 times a negative 2 be a negative 10 slope. Wow, really steep, okay? And so on. The higher you go, the steeper and steeper it gets, always negative. So let's go below, like negative 1. Negative 1 times 3 minus a minus 1, which is 3 plus 1 is 4. So that's another negative 4 here. Really steep negative slope here, just like we had above. Okay. Very steep. And when you go to negative 2, you have a negative 2 times a 5, so that's negative 10. So here you are, extraordinarily steep again, just like we saw above. Okay, very, very steep. And they just keep getting steeper. Well, what are the curves that are in here? Well, near 0 is near a 0 slope, then they go up and then go back to a 0 slope. So basically your curves look like this. Never reach that y is equal to 0 or y is equal to 3. And up here they're coming down really steeply, going like this, really crashing down there. Okay, and here moving quite far south really quickly. Okay, so there's your curves. Okay, now side. I mean, they go through blah, 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 blah. But I think what their point is here, all these curves are parallel to each other. Whether you're above y equal 3, between 0 and 3, or below y is equal to 3. So basically, these correspond to something like y1 is equal to, y1 of x is equal to y of x minus k, where k is a constant, also a solution. So basically that gives you a family of solutions, where k is your constant doing that. Now, out of the blue, okay, they say to verify that this is a solution. And the solution they give is y is equal to e to the x. Okay? Oh, yeah, let's see. Is this the same problem? No, different problem. Y is equal to e to the x. Okay. So I'm going to take this off. I don't know. I mean, that was fun, but I mean, they're just trying to emphasize that whatever you get as a solution for your problem, if it's not an initial value problem, and you got a constant of integration, it's going to be of the form y is equal to x plus or minus k, where the k is the constant of integration constant, basically. Okay, so let's erase this. And I don't think I need a graph for this last, so let's go to this page. Let's say we have y of x equal e to the x. Okay? And that's good because e to the x is defined everywhere from negative infinity less than x less than positive infinity. Okay? Because that is true everywhere. Okay? I think I have a student coming in. Yes! Goodness, I'm tired of talking to myself. Okay, Marcus is here. Let me get things turned around. I've been recording, but I haven't been projecting because I want to see it. Maybe if you're not getting here, huh? Okay. taking a few minutes to warm up, brighten up. Okay, I'm on page 43, the very bottom of the page. Now, where we left off last time was a little above the middle of the page, autonomous differential equations of direction fields. We basically knocked that around quite a bit. Translation property, which I know the reason they do it, but it wasn't very clear why they did that now, but it was fine. And right now we're at the very bottom of the page. I will read that red print again. If y of x is a solution of an autonomous differential equation, dy dx is equal to f of y, then you know automatically that y1 of x, okay, is equal to y of x minus k, where k is a constant is also a solution, which means for an autonomous differential equation, your constant of integration is going to always go with the x plus or minus k, okay? Now, that said, we were just going to do this is in the line below. If it's easy to verify that this y, e to the x, is a solution for this initial value problem, dy dx is equal to y. Okay? Really easy to, all right, let's get the other part, where y of 0 is equal to 1. Okay, there's your initial condition. Okay, now, real easy to verify, because if you do dy dx, you get what? Yeah, y of x is e to the x. Take the derivative of that. Yeah, up at y of x is e to the x. Take the derivative of it. E to the x, exactly, right? And what is e to the x? E to the x is y. So yeah, that works, but it must also meet the initial condition. If you put a 0 in, y of 0 is e to the 0, which is, say again? Yeah? Nope. Anything raised to the 0th power is 1. Okay. And sure enough, the initial condition is met. So yeah, that's the solution. Okay? Now, if you're looking for another, say, y1 of x at a different initial condition, say, same problem here, this one right here, except now your y of 5 is equal to 1. Okay? So again, e to the x works for your differential equation, but y of 5, which would be e to the 5th, is not 1, okay? So if that has to be 1, then what you have to do is make it y minus 5. You see? Then if you plug in a 5, then you get a 0 here, and that will make it 1. So basically what you find out then is that the one for this initial condition would be y is equal to e to the x minus 5. Okay? And that will make the initial condition true. And what is this compared to that? It's a horizontal translation. 5 units to the right. And that's also good for all negative infinity less than x less than positive infinity. all values. Okay. That ended the 2.1. So homework exercises here. Do either one or three or both. They have 4 parts, so I would do some of each of them. They give you the direction fields for those problems, so that will be helpful, I think. Then do any of the odds 5 through 11. Do 13. Do 15. Okay? And then discussion problem that's completely up to you. Under 2.1.2, that was all 2.1.1, then do 19 and any of the odds 21 to 27, do 29, and then there's some discussion problems if you're interested in those. There's also some mathematical models. If you're interested in those, you can do those. But they're not required, they're just possible. Okay, now, all right, we've had autonomous differential equations. What's the rule to be an autonomous differential equation? And by the way, we're dealing with, this chapter is first order differential equations. Say that again.
Independent values do not appear.
Independent values do not what?
Variables.
Oh, okay. Is not on the right-hand side.
Yeah.
So you have dy dx, first order differential equation. When you get everything except that on the other side of the equation, there can be no x dependence there. If this is dx dt, there's no t dependence there. You know, whatever your independent variable is in the denominator here, that cannot show up on the right-hand side. So in other words, it's a function of y alone or your dependent variable alone, your right-hand side. When you isolate the dy dx, or whatever your y prime, whatever it is that you have here, first order, get that alone here, everything on the other side is a function of your dependent variable only. No independent variable dependence there. All right, let's move to generally, I want to say this, generally, this is the first thing I look for when I'm trying to solve a differential equation. First, check and see if you can separate the variables, okay? And you call those separable equations, okay? Consider the first order differential equation dy dx is equal to some function of xy. Okay. If there is x dependence, this is not autonomous. So we got an equation that's not autonomous here. Okay? Now, when f does not depend on y, in other words, if it doesn't depend on x, you got an autonomous equation. If it doesn't depend on y, then you would have dy dx is equal to some, and for some reason they changed the thing, g of x. Okay? Now, I know a pure mathematician would just go crazy if you say this wrong, but I'm going to try to say it correctly. What you want to do in this case is write this in differential form. That's a lot better than saying, this is what you never say, multiply both sides by dx, okay? The reason you don't say this is not a ratio. It looks like a ratio, it looks like a fraction. It's not, it's an operator. So therefore the correct way to say it is write it in differential form, which would be this. Does this look any different? dy is equal to g of x dx. Okay? Sure looks like you multiplied by dx. You didn't. You wrote it in differential form. Okay? For the pure mathematician, they would cringe at saying multiply both sides by dx. So don't say that. You can think it if you want to, but don't say it. Okay. Now, what can you do here? Integrate both sides of the equation. This integrates to be y, and this integrates to be some g of x plus c. Right? Now, that's assuming this is integrable. And if it is integrable, then it's going to be something like that. Okay? And there you have your solution. Done. Okay? Done. Okay. So here's a definition. You got your book, right? Do you remember if Megan has a book? I don't recall. Huh? Oh, she does. Okay, she has a e-book. Okay, I see. All right. A first-order differential equation of the form dy dx, and we're going back to our first thing, that's you can write, instead of this f of xy, so let's back off a little bit here. We're going back to this form here. Okay. If you can take this form, this xy, function of xy, and separate it into some g of x and h of y, in other words, take that function and make it into a product function where one product only has the x dependence, the other product only has y dependence, then this is what we call separable. Okay? And here's how you would do that. Okay? You would write it in differential form. dy is equal to g of x, h of y, dx. Okay, that's in differential form. Then divide both sides by h of y. Now guess what you got? You got a y's on the left, x is on the right. No crossover anywhere, integrate them separately. Okay? Whatever this function is, you might need to do exponentials, you might need to do logarithms, you might need to do integration by parts, you might need to do partial fractions. Whatever you have to do to get this done, do it. Okay? And then whatever you have to do there. If it's g is an integrable function, integrate it. Okay? That's called, this is said to be a separable differential equation, or to have separable variables. Okay? So let's take a look at some of those, and see if they are indeed separable. All right, here's an equation. dy dx is equal to y squared x e to the 3x plus 4y. Now, at first glance, would you say that's separable or not? What's that? Okay, how would you do that? Say, I know I can separate the y squared from the x. That's easy. They're multiplied by each other. Yeah. What do you do about the e to the 3x plus 4y? Well, that's a rule of exponents. E to the 3x plus 4y is the same as e to the 3x times e to the 4y, right? Anytime you have the same base, different or even same exponents, multiplied together, keep the base, add the exponents. So this is exactly that. And when you do it that way, then I'll write this dy equal this dx, that's in differential form, okay? And then we want to divide our y squared e to the 4y out, move it over here, and sure enough, you have a separable, you have separated the variables. You got a big problem, okay? Integrating this is not a piece of cake, okay? And you might have to do a bunch of stuff to try to get that done. This one's not nearly as bad. What would you use here?
X e to the 3x.
E is x e to the 3x. Yeah, what technique would you use with integration? See, what you're going to do is integrate both sides of the equation. Okay? Let me clean it up, make it a little nicer. The integral of dy over y squared e to the 4y is equal to the integral of x e to the 3x dx. Okay? Like I was saying before, this is not pretty, okay? This is not a particularly easy thing to do. Actually, it's not too bad, now that I think about it. Rewrite this side to be the integral of y to the minus 2 e to the minus 4y dy. And that's equal to, did you ever decide what to do on the right? Second. Okay. So product by parts, integration by parts. That be u and that be dv. This becomes, du becomes dx, and that becomes 1/3 e to the 3x. Okay? And that you can do. Doing this at least makes you think you can do something similar. The trouble is, taking the derivative of this isn't making it any better. I'm a little bit at a loss. I would try a few things. I don't know if we should take class time to do it. And try a few things to do. First, I might say, let u be minus 4y. Okay? And then du would be minus 4 dy. Okay? Not particularly great, but then once you've had that, when you said let u equal minus 4y, then du is equal to minus 4 dy. Okay. Pretty straightforward. Okay. I don't know if this will work, but here's what I would try next. Rewrite this as y is equal to minus u over 4. And then y squared would be minus plus u squared over 16. I don't know if this is going to work, but let's try it. Then you would have the integral of, I'm sorry, it should be y to the minus 2. Yuck. Okay. Let me erase this. Okay. Y to the minus 2 would be minus u over 4 to the minus 2, which would be minus 4 over u. Keep wanting to write y's. That's ugly. That's ugly. This is ugly. Okay. So let's clean that up a little bit. It's a u and this is a u. Okay? And this thing would then be squared, which would be 16 over u squared. Okay. Then what would your function be? You'd have a 16 in the numerator, a u squared in the denominator. That's your y to the minus 2, and that would be e to the u up here. And then you have a minus 1/4 out here. When you do divide this by minus 4 and divide this by minus 4. That would give you your du then. Du over minus du over 4. That hasn't made it much better at all. Okay? Okay. A real pain. Let's see. They didn't do anything with it. Silly them. Okay, I think that one would only be one. Even though it's separable, you can't integrate. Okay, but at least that gives you a starting point. Let's do something else. How about this one? dy dx, first order differential equation, is equal to y plus sine x. Is that separable? Say again? How? Okay. Okay. All right. Now, what I thought I understood you say is write it in differential form. dy is equal to y plus sine x dx, right? And then I hear you say divide by y. Okay. Sure enough, that will go out, but you still have plus sine. That would be dy over y would then be equal to 1 plus sine x over y dx. That's not separable. You still got the y in there. Only way you can do this if that had been a times or even a divided by. But with a plus or a minus there, Now, a plus or a minus in an exponent, yeah, you can make that separable. But not when it's just written out like this. So that is not separable. The first one is, the second is not. Okay? Now, okay. Can't see anything else different. They, for some reason, introduce a p of y, which is 1 over h of y. That makes no sense to me to do that. Oh, okay. So, what's that? Okay, yeah. It'll be out there possibly before the morning's over. I don't know. It just depends on how fast it uploads. Okay, I'll keep going. Okay. Now, for some reason in the book, they want to rewrite the 1 over h of y to be p of y. And they say that reduces to equation 1 when h of y is equal to 1. Of course it would. Okay. Now if y is equal to phi of x, not really sure why they're doing that. Okay, it's some function of x. call it phi, whatever, represents a solution to, I've got to get, lost most students and now in here by myself, so I better write more of this down. Goodness gracious. In addition to a sore throat over the weekend, I got conjunctivitis in my left eye and put drops in it last night, slept with no problem, put them in this morning even though it wasn't hurting, but it never fails after about an hour or so of straining my eyes, reading and that kind of stuff. Here it comes hurting again. I don't think it's as red as it was, but it definitely has some issues. And that's why I think I may have a low-grade sinus infection, because I think maybe from blowing my nose or something like that, air went up toward my eyes and may have infected that eye. I don't know, but I'm having trouble seeing, so sorry about that, in addition to having trouble talking. So really a pathetic situation here. All right. So what we have then, what you had initially was dy dx is equal to some f of xy. And we said if we can make the f of xy a g of x times a h of y, okay, if we can separate the variables, then we can proceed. Well, what you would have then, when you write in differential form, as we did before, is dy over h of y is equal to g of x dx. Okay? Now, what they did is rewrite 1 over h of y to be p of y. And for the life of me, I mean, there probably is a reason, but now it looks like this. P of y dy is equal to g of x dx. Okay? Now, that looks nicer for integrating purposes. Okay? All right. But now they're going to make an assumption here, and the assumption is y is a function of x, of course. So let's say y is equal to some phi of x. Why they jump to Greek letters, there's no reason. There's nothing special about it. It's just y is equal to phi of x. And if that represents a solution to, okay, I'll rewrite this equation to be p of y dy dx is equal to g of x. That was the thing I would have had before I put it in differential form. Okay? If that phi of x is a solution to that, okay, we must have it seems like they're going around their elbow to get to their ear here. If this is true, then this implies that dy dx is equal to phi prime of x. Changing notation is all they're doing. Okay? Now, if you substitute the y, phi of x, then this has you that p of phi of x, okay, times dy dx, which is phi prime of x, from here, okay, this is equal to g of x. Okay. I'm not really sure why they're doing all this. But then we integrate both sides. This is now all a function of x, and this is all a function of x. We have lost our y dependence, okay, anything to do with that. But now they go back and do the same thing, and I swear, for the life of me, I do not see why they introduced the phi of x or anything else, because now they go back and say this is the same as the integral of p of y, because y is that, and your phi prime is merely dy from up here, okay, and this is equal to the integral of g of x dx. Okay, now that I think about it, notice they didn't say write it in differential form, even though they sort of did. They wiggled their way around it, but they've gotten the same thing that I was going to say here is integrate both sides. Okay, write it in differential form and then integrate. So they went through all this to avoid saying write it in differential form, to convince you that was differential form. Okay, and so this they're saying could be some capital H of y, which I find a strange way to express that, is equal to some g of x plus some constant c. If I were doing this, I'd make that a capital P, not a capital H, okay? Because the H we used up here, and this has nothing to do with that. That's not the antiderivative of 1 over H, it's the antiderivative of P. So why they did that, I'm not sure. So this suggests to you a procedure for solving separable equations, okay? A one-parameter family of solutions, usually given implicitly, is obtained by integrating both sides of some function of y dy is equal to some function of x dx. Note there's no need to use two constants of integration for separable equations, because you just add them together or subtract them or whatever and they become one. So, boy, they made a pretty simple concept very confusing. Well, not that confusing, but why do it? So here is an equation. 1 plus x, this is example 1, dy minus y dx is equal to 0. Now that is a differential equation. I don't suggest that you go back and write it as a differential equation. It is. It's got dy's and dx's in it. Okay? Now, what you want to do is separate and get all of one on one side and all of the other. So let's at least get our dy's, leave it on this side, 1 plus x dy, and add this y dx to the other side, and you have this equal to y dx. Okay? Well, I don't want this 1 plus x over here, so I'm going to divide by 1 plus x, which means I divide this side by 1 plus x. But I don't want the y over here, so I'm going to divide that by y and this by y. 1 plus x's go out, the y's go out, and here you have dy d over y is equal to dx over 1 plus x. Now we integrate both sides, okay? And this I hope you recognize as natural log of y, okay, is equal to the natural log of, and I think here you have to put, and maybe even here, you have to put absolute values around 1 plus x, okay? And then you put your plus c, okay? Now, that looks like a perfectly good answer, and it is an okay answer. However, before I go anything else, they're looking ahead, and they made that C1, and there's a reason for that. They're going to take the exponential of both sides of this equation. E to this, E to all that. Okay? We know the E of a log, natural log, is y. So that you want to say absolute value of y, and that you really should. Okay, now this right-hand side, again, because of the exponent, property of exponents, if you have a base with a sum, then you can make that as the same base with the product. So this would be e to the log absolute value of x plus, it's 1 plus x, but x plus 1, it doesn't matter. Okay, e to the c1. Okay? Well, this becomes absolute value of y equal absolute value of x plus 1 times some constant. E to the c1, so c1 is a constant, that's just a constant, let's call that c. Okay? Now, at this point, they do a little scratching on the side over here, and by looking at that absolute value and breaking it into its various parts, and they're still putting 1 plus x, so I'll go back and say 1 plus x. It really doesn't matter. That makes the right-hand side either a plus or a minus. Okay? With the problem is you can incorporate that plus or minus into your constant and then go back to just being, and I probably shouldn't have done this quite so soon, y is equal to c e to the, x plus, okay, let me go back and do it the same way they did. Sorry about that. Okay. 1 plus x. Okay. And there is your solution. Now, want to check that? Verify that? Do dy dx. Dy dx is equal to c is equal to okay. This is not particularly filling here because that would just be C. And that's not what we had before. If we had rewritten this, that would have been dy dx is equal to y over 1 plus x. Which is not the same as C. So this is, oh, well, it sort of is. C is equal to y over 1 plus x. Yeah, it is. Okay. So yeah, rather strange, but true. Okay. But you said C was a constant, but now you've just labeled it as having dependence of x and y, but separately. Okay. Now, let's go to another example. I wish I hadn't tried to verify it for you there. That made it actually more confusing. This is an initial value problem. We will not have a constant of integration in it. Initial value problem dy dx is equal to minus x over y. Okay? Where y of 4 is equal to negative 3. All right. how would you go about solving this? Well, again, what you want to do is separate your variables, which is write this in. After a while, I think you'll get to doing, because I do it too, write it in differential form and separate the variables at the same time. So multiply both sides by by y while you're writing in differential form, and you get y dy is equal to minus x dx. I hope you see that, okay? Take it as many steps as you need, but if you do, you'll see that's what it comes out, okay? Integrate both sides of this, and this gives you y squared over 2 is equal to minus x squared over 2. Okay? Plus some constant c. Okay? Now we plug in what our initial condition is. When x is equal to 4, y is equal to negative 3. So this will be 9 halves is equal to minus 8. 16 over 2 is 8 plus c. Okay? So this is 4.5, if you want to call it this way, is equal to minus 8 plus c. So add 8 to both sides, and you get c is equal to 12.5. Or if you want to write that in fraction form, 25 halves. Okay? So your solution is, let's multiply both sides. Well, okay, let's write it down first. Y squared over 2 is equal to minus x squared over 2 plus 25 halves. Multiply everything by 2 and you get y squared, I'm going to bring it over here, plus x squared is equal to 25. Well, that's a circle of radius 5, isn't it? Okay? Or at least half of a circle, because and it would be the bottom half, because that would be radius 5, but when y of 4, 1, 2, 3, 4, 5 is minus 3, that puts you down here. So here's the half a circle that you're on. Okay? Now, I guess if you were writing this, once you got it in this form, leaving that over here, this would be y squared is equal to 25 minus x squared. If we had left that over here, multiplied by 2, then y would be plus or minus the square root of 25 minus x squared. And there's where you find out you have to go with the minus. So, and that's what gives you the lower half of the circle. Y is equal to minus the square root of 25 minus x squared. Okay. Because you plug in a 4 on the right hand side for the x, that'd be 25 minus 16 would be, 9. Square root of 9 is 3. Minus sign makes it a minus 3. So yeah, that's how you determine, that's the function that you use. Okay. Sorry, my eyes are hurting like crazy, especially my left. But I said it wrong before. My left eye is the one that had conjunctivitis. So anyway, I may have to take a break and just go. I don't think rinsing the water is going to help, so I'm going to try to just live with it for a bit. Okay. There is a little blurb in the middle of page 49 that's talking about losing a solution. Some care should be exercised in separating variables, since the variable divisors could be 0 at some point. Specifically, if r is a zero of the function h of y, then substituting y equal r into dy dx makes both sides equal to 0. In other words, y is equal to r is a constant solution of the differential equation. Okay? But after variables are separated, the left-hand side becomes dy over h of y is equal to g of x dx. That's undefined when, at r. Okay? Because if r is 0 and you're if h of r is equal to 0, then that's undefined. As a consequence, y is equal to r might not show up in the family of solutions that are obtained after integration and simplification. Recall that such a solution is called a singular solution. So that's the warning. Okay? Let's do example 3. I just have a sneaking suspicion it's going to have something like that you're dealing with. Let's see if it does. Here we have dy dx is equal to y squared minus 4. Now, if I were to ask you what kind of differential equation this is, of course it's the first order differential equation. Everything in the chapter 2 is the first order differential equation, at least so far. I think it better be because that's the name of the chapter, first order differential equations. But if I were to ask you to classify this one, not according to that, it's ordinary, it's first order, we know all that stuff. Not linear, we know that too, okay? But you could either talk about this as being autonomous differential equation because the right-hand side is a function of y alone, not x at all, but it's also a separable differential equation, okay? In fact, if you think about it, all autonomous differential equations, by definition, have to be separable because there's no x over there. Just write it in differential form and divide by your function of y, and you got y's on one side and x's on the other side. So if you're doing separation of variables, this would be dy over y squared minus 4 is equal to dx. That's it. Now if you were to integrate both sides, integrating the left-hand side requires partial fractions. Okay? What you have there is the integral of dy over y plus 2 times y minus 2. And that's equal to x. Okay? I'll go on and put my plus c out there clearly because the integral of dx is x. Okay? So that's what we got on the right side. Okay. Let's deal with this part. This is can be written partial fractions a over y plus 2 plus b over y minus 2, and you want that to be equal to 1 over y plus 2 times y minus 2. Okay? You're looking for your a's and b's here. Goodness, my eyes hurt. Okay? Well, the trick here is to multiply both sides of the equation by y plus 2, and that yields you, no, I'm sorry. Multiply both sides of the equation by your denominator. Okay, and that would give you a times y minus 2 plus b times y plus 2 is equal to 1. Okay, check that out, see that is indeed true. Okay, then what we do is put y equal 2 in here, and that wipes out your a value, and that gives you that b times 4 is equal to 1, so b is equal to 1/4. If you put a y is equal to negative 2 in, that would give you a times negative 4 is equal to 1, so a is equal to negative 1/4. All right. Yuck. This is pretty miserable. Okay. Now we want to integrate this thing, which was the same as that thing, dy, but we're going to put in those values. So this would be the integral of, and I'm going to put the b first because it's positive, 1/4 dy over y minus 2 minus 1/4 times the integral of dy over y plus 2. Okay, well, I put a parenthesis there, but I did. Okay. Whew. This is 1/4 the log of absolute value y minus 2 minus 1/4 absolute value, log absolute value y plus 2. Okay. Now we don't need to do a plus c because we've already done that. So let's see what our solution looks like then. There's the left, there's the right. So we have real tempted to just multiply everything by 4. Get rid of, let's see. Let's try that and see what happens. Log of y minus 2 minus log of y plus 2 is equal to 4x plus, now I should have been keeping up with the c's. It's a new c, it's not the same c as before. You could have called the first one c1, this will be c, whatever. Okay. Now, that's one possibility. You could also write this as log of y minus 2 over y plus 2 is equal to 4x plus c. Okay? Or you could take an e of both sides, which would be y minus 2 over y plus 2 is equal to, now the e to the c can come around and be another constant c, different from the previous c, e to the 4x. Okay? I don't know if there's a simpler way to write it. To me, that's about as simple as you can get. But I know there's a possibility here that you got some problems. For instance, y cannot equal negative 2. Pretty obvious. But in the original problem, it couldn't either. Well, let's see. If y was negative 2 in the original problem, that's dy dx is equal to 0. And of course, that would be y is equal to any constant. Okay? And I don't think they gave us a boundary value. So, by the way, trying to find my final answer. I know I did it here. Yeah, right there. We'll do okay. All right. Yeah, they did change it somewhatly. Okay. And here's how they did that. I put the C in front, and by the way, to get rid of the absolute value bars, they do plus or minus, okay? I put the C in front of the 4x. They waited to do this later, okay? Okay? And then what they did is this. Y minus 2 is equal to I'm going to leave the plus or minus in there for a bit. CE to the 4x times y plus 2. Okay? I'm going back off of that. They've already taken out the plus or minus. They let the plus or minus fall in the C. Okay. So, I think, okay. So here's what we're going to do. I have a feeling that something is going to come back and bite me, but let's see. This will be y minus 2 is equal to y times c e to the 4x plus 2 c e to the 4x. Okay? Let's subtract this from both sides. That's minus c e to the 4x y. Just rearrange the order here. And we're going to also add 2 and subtract c e to the 4y. 4x times y. Okay? So that gives you, factor out the y's, and that gives you 1 minus c e to the 4x. Okay? And this is equal to 2 plus 2 c e to the 4x. Okay? Because you subtracted this one out and you wound up with that, which then would be y is equal to, factor out the 2 here, and you would have 1 plus 2c e to the 4x over 1 minus 2c e to the 4x. And that's what they got in the book. Okay? Wait. Not a 2 there. Not a 2 there, not a 2 here. We factored out the 2. 1 plus c e to the 4x over 1 minus c e to the 4x. Okay? Now, all right. Now, let me write my answer over here. Y is equal to 2 times 1 plus c e to the 4x over 1 minus c e to the 4x. Okay, there's my solution, there's my parameter. Everything looks hunky-dory. Okay, now, if you put in, and this is what they're saying here, if you go back to the original equation, like I said before, y is equal to 2 and y is equal to 4, make the right-hand side equal to 0, and dy dx would then be equal to 0 if y was 2 or 4. Those are two constant equilibrium solutions, y is equal to 2 and y is equal to minus 2. Okay? If you put the c equal, okay, like I said, this is y plus 2 times y minus 2. So y is equal to, y is equal to. If you put c is equal to 0 here, you get y is equal to 2. Okay? So with a choice of c equals 0, you do get y is equal to 2. Steady state constant solution. However, there's nothing you can do, no value of c you can put in there that will make y equal negative 2. Not in this solution. Okay? That would mean this thing here has equal negative 1, and I don't think there's any way to make that equal a negative 1. So that is one case, that's a singular solution. Doesn't come from your parameter c. The y is equal to plus 2 could, but not the y is equal to minus 2. Okay. So they go on and on about that, but I don't think it's a huge consequence. Okay, I'm going to erase all that, and I'm going to have to run down. I hate to do this, but run down and get something for my throat. So I'm going to put this on pause right now. Well, I'm back. Sorry, it's gone longer. I forgot to turn on the light. I'll be right back. All right, that was a longer delay than I wanted it to be. Really not feeling very well, and but I think I can finish the class, so let's move on with it. Okay. Let's look at example 4 now. Sorry. Here's your equation. E to the 2y minus y cosine x dy dx is equal to e to the x, no, e to the y sine 2x. It's an initial value problem, sorry, where y of 0 is equal to 0. Okay. Now, where would you begin? Well, you have products on both sides of the equation. The first product here depends on y only. The second product only on x. Then you dy dx, you can write it in differential form, which is fine. On the right-hand side, you have a factor e to the y depending only on y, and sine 2x depending only on x. So yeah, we can separate these two. So we want the y's to stay on the left and the x's to go to the right, including the dx, writing in differential form. So that will lead us to have e to the 2y minus y. We're going to divide out the cosine x, okay? Okay? And we're going to divide out e to the y. And these go away, and that leaves our dy here is equal to sine 2x over cosine x dx. Okay, writing it in differential form. All right. Now we can do something with this. This will be e to the y, because e to the 2y divided by e to the y is e to the y, minus y e to the minus y. Okay, I'm going to write it like that. Okay, and this will be times dy is equal to, and here, somewhat of a pain in the neck, but if you recall, sine of 2x can be written as 2 sine x cosine x. Now, let's see if they have any of those tables anywhere in your book here. Don't think they do, not at this level, okay? So it's just something you need to have remembered. Your identity for sine 2x is 2 sine x cosine x divided by cosine x, and obviously that wipes out your cosine x's, and this is your dx. So this makes it a little more palatable, okay? The left-hand side still is a little bit of a problem. Not all of it is, but part of it is. So let's rewrite this as the integral of e to the y dy, that's the first part, minus the integral of y e to the minus y dy, okay? And that's equal to 2 times the integral of sine x dx. Buy that? All right. This is pretty simple. This is e to the y. Okay? Now, this is an integration by parts. Okay? Let u equal y and dv equal e to the minus y dy. Then du is equal to dy, good, and v is equal to minus e to the minus y, right? Yeah. Okay. So, let's take just this integral here and bring it up here. And this will be a minus, because this minus is still there. uv, which will be y, and it has a minus, so that makes it a plus, e to the minus y. Okay? Now we have a minus times a minus times a minus. So the second part is a minus the integral of v du, which is down here, and that would be e to the minus y dy. Okay? So this will be y e to the minus y plus e to the minus y. Okay. So that's what the second part gives. So what we have here is a e to the y from here plus y e to the minus y from there plus e to the minus y. That's the left-hand side. Right-hand side is minus 2 cosine x. It's equal to, I left off my equal sign, equal minus 2 cosine x And then we can put a plus c there if we want to. Okay? Now, initial condition where x is 0, y is 0. So what we have here is a 1 plus 0 plus 1 is equal to a negative 2, because cosine of 0 is 1, plus c. So you have 2 is equal to minus 2 plus c. It looks like the c is equal to 4. So what's our solution? E to the y plus ye to the minus y plus e to the minus y is equal to minus 2 cosine x plus 4. All right. Now, don't believe there's any way in the world to isolate the y. I can't think of any way. Let me see if they have some. Nope, I think that's what it is. Okay. They have e to the y plus e to the minus y plus e to the minus y, and then they put the 4 in front is equal to 4 minus 2x. Okay. Can't solve that explicitly for y at all. You look at that differential equation we started with, not too much chance of that ever being solvable just for y, because that was one complicated looking mixture of things. All right. Separation of variables can do quite a bit for you. Okay? Now, the use of computers. There was a remarked section at the end of section 1.1 that mentioned it may be difficult to use implicit solution g of x, y equals 0 to find explicit solution y is equal to phi of x, that kind of stuff. I don't know where they're going with this, but they're talking about a computer algebra system, which we don't have. The function of two variables z is equal to g of x and y, both. Gracious. The two-dimensional curves defined by g of x, y is equal to c, where c is a constant, are called the level curves of the function. With the aid of CAS, computer algebra system, some of the level curves of the function g of x, y is equal to e to the y plus y e to the minus y plus e to the minus y plus 2 cosine x, bringing that over. And they did it for equal 4 because that's what our initial condition was. Went through 0, 0. And sure enough, there is a curve in your family of curves, and that's the level curve for c is equal to 4, which is 1 in our problem, but they drew another one, c is equal to negative 2. Why they chose that one, I don't know, except it was just convenient on the page, I guess. Okay? That illustrates the level curve g of x, y is equal to 4, which is a particular solution of the differential equation there, which is a member of that bigger family. Okay. Still don't see a lot of explanation why they're doing so much of this. Okay, let's look at the top of the following page. If an initial condition leads to a particular solution by yielding a specific value of the parameter c in a family of solutions for a first-order differential equation, there is a natural inclination for most students and instructors as well to relax and be content. However, a solution of an initial value problem might not be unique. They say example 4 of section 1.1 was one of those. Okay, let's take a look at that again. Here was your issue, initial value problem. The differential equation part is dy dx is equal to xy to the 1/2. Okay? And y of 0 is equal to 0. Now, it says it has at least two solutions, y is equal to 0 and y is equal to 1/16 x to the 4th. I think I remember doing this now. Yeah, we came up with two possible solutions there. We are now in a position to solve the equation. We can do that. They did it for us before, but we're going to do it now. Separable variables, because it's a product that you can separate the two. And this gives you dy over y to the 1/2 is equal to x dx, subject to y0 is equal to 0. I would rewrite this as y to the minus 1/2 dy is equal to x dx, then integrate both sides. Okay? God, that's my eye. Itches. It doesn't hurt so much as itches, but I can't scratch it or else it hurts. Okay, so this will be a y to the 1/2 times 2, right? When you antiderivative of y to the minus 1/2 would be that, because if you were to then take the derivative of that, 2y to the 1/2, that would be 1/2 times 2, which is 1, y to the minus 1/2, which is exactly what you got there. This is equal to x squared over 2 plus some constant c. Now, y is equal to 0 when x is equal to 0, so that would give you c is equal to 0. Okay? So that would give you your solution to be, let's see, y to the 1/2 is equal to x squared. Goodness gracious, my eye hurts. I guess the better way to do it would be y to the 1/2 is equal to x squared over 4, and then y would be equal to x to the 4th over 16, which is certainly one of the solutions we got before. Okay, 1/16 x to the 4th, but I don't see where the, yeah. Now, where they say you lost the trivial solution, which obviously, if you look above, from x equals 0, y is equal to 0, okay? I'm sorry, y is equal to 0 is a solution, because that way when x is 0, that's still a solution. But you see, they say that you lost it when you divided by x to the 1/2, because obviously y can't be 0 if you're dividing by 0, okay? So you kind of lost that one there, okay? And I guess that's their only point. It says it actually has many more solutions. It says for any choice of parameter a, the piecewise defined function satisfies both the differential equations and the others. So again, they're throwing this at you without a lot to do with it. You know, they're just saying there's an infinite number of solutions that fit the initial value problem. There's not just one anymore. There's an infinite number, and here's what they claim it is. Y is equal to piecewise defined 0 anytime x is less than a, and it's equal to 1/16 x squared minus a squared squared, okay, anytime x is greater than or equal to a. Gracious, my eye hits. Now, I can't quite figure, it's just a trivial point. Why didn't they say y is equal to 0 when x is less than or equal to a? Because when x is equal to a in this bottom one, you get 0 too. So I would have put the x less than or equal to a, and then to be the 1/16 x minus a, x squared minus a squared squared anytime x is greater than a. It really doesn't matter. They're 0 in every place. All right. Oh man, we're out of time. We're going to begin next time. Sorry, I had the delay in the middle of the class. We'll begin next time with this an integral defined function, which sort of sounds like a pain in the neck, but it's not too bad. Last thing we cover in this section. So homework exercises, do any of the odds 1 through 21. Any of the odds 23 to 27. Do 29. Either 31 or 33. Any of the odds 35 through either 35 or 37 or both. Think you can do either 39 or 41 or both. Try 43. Probably stop there, and we'll pick up those last few next time. Good deal. Sorry about that. I had to take a delay in the middle, but we're almost finished 2.2. We'll move on from there.